Hello, I'm Cheryl Nod, Research Manager for the Baltimore Neighborhood Indicators Alliance at the University of Baltimore. In this video, getting started with geographic information systems, I'm going to be covering some geospatial concepts for social science applications for the Baltimore Data Science Corps in 2022. In this presentation, I will be covering a bit of information about projections and coordinate systems, what is a GIS, the geocoding process, using point level data, and then aggregating it and normalizing it to create community indicators. I'll have a bit of an introduction to some geographic boundaries, and lastly, wrap up with some online resources. So free software options for students and the public, as well as places to get data that can be used in AGIS. So let's start off with thinking about the globe. So the planet is a three-dimensional surface. We are on the sphere, and the study of geography is the study of the planet and all of the people, the animals, the systems that interact on this Earth. Map making and geographic information systems is a way to represent this three-dimensional surface on a two-dimensional plane instead. So for mapping, there's a lot of different ways and sometimes a lot of opportunities and caveats for displaying this 3D surface on a 2D plane. Here with this graphic, we can see three different ways that the three-dimensional Earth can be represented using azimuthal, conic, and also cylindrical projections. Each of these ways of representing the Earth into a print map or an online system requires you to select what is the most important facet for your map. So when you're doing this representation, you oftentimes have to pick what is your highest priority, maintaining the shape of landforms, having accurate distance, accurate direction, or also accurate area. So each of these projections, and there are many projections, have these caveats. And so at the Baltimore Neighborhood Indicators Alliance, we analyze a lot of data that is very specific to Maryland. And so we use a Maryland specific projection, a conic projection, similar to this one in the center, that allows for the greatest level of accuracy and representation as we're analyzing our data. It is incredibly important of having a clear sense of what projection and what coordinate system you're using, because it enables you to ensure that you're using essentially the same units of measurement, the same geographic projection and specifications when you're doing analysis. So in order to really harness geographic and spatial location information, we rely on Cartesian coordinate systems. These, which you may have become acquainted with in middle school or high school or college algebra, is a way of using X and Y planes to identify places. So thinking about your distance from the y-axis or the x-axis. In this graphic here, we can see that the intersection of the x and y axis is represented as 0, 0, meaning it is at the center. There is no distance in terms of on the x-axis or the y-axis. In this coordinate that is in this particular quadrant, we can see that it is 2 units along the x-axis and 3 units along the y-axis. Conversely, we have on this other quadrant a location that is 3 distance units to the left of the y-axis, so it's being represented with a -3, and it is 1 distance unit above the the x-axis, giving it a number of 1. So if we think about then plotting out these specific locations onto a coordinate system, we're able to then calculate the difference and the distance between points that are mapped on here. So we can think about What is the difference in the distance of this particular represented in red location versus this one that is in blue versus this intersection versus the one in this particular quadrant? And so thinking through distance is incredibly important for us to identify patterns, to identify trends, to identify any sort of spatial information. And so one way for us, as we're thinking about representing that three-dimensional surface onto a two-dimensional plane, is really using this Cartesian coordinate system and treating the latitude and longitude systems with their equators and prime meridians as your X and Y axes. So thinking about the equator as the X axis and thinking about locations that are north and south of the equator as receiving positive or negative values. And for longitude, using the prime meridian as a y-axis and using east and west locations in relation to the prime meridian as getting positive and negative numbers. One way that we describe latitude and longitude is in decimal degrees. So thinking and making the shift from algebra to geometry. So what is your angle? What is your distance between the equator and the north and south poles? At what angle is your data that you are using to represent something on the planet located at? So in this little box in the upper left-hand corner, I've got a couple example decimal degree locations of the X and Y axis that are representative of locations in Baltimore City. So Baltimore City is north of the equator. So we have we've got a positive uh, value for our Y value and negative for X, meaning that we are located north of the equator, we are located west of the prime meridian. You see here, we have a lot of decimals in this particular coordinate. When we're thinking about the Earth, it is a very large place and specificity often matters. So in this case, when we're looking at decimal degrees, or sometimes map projections come in feet or meters, you want to have a lot of decimals. Decimals mean more specificity on your location. If, for instance, you only have data and values that are going out to the tenths or hundredths place, there's a lot of variation that could be captured within there. So if you are trying to represent something in the real world that can be related to a particular address, a particular location within a city, you want that specificity. So we finally arrived at our question. What is a GIS? So geographic information systems are a system for managing, visualizing, and analyzing spatial data and information. So you are able to pull in information from a variety of sources. In this graphic here, we can see some examples of different data layers that we can use in a GIS, such as political boundaries, elevation data, geographic names that can be used in labeling, hydrography, so water bodies, land cover, orthoimetry, structures, so physical buildings that humans have created, and even transportation lines, so street networks, public transportation routes. And so with GIS, you're able to pull in these pieces of information and they are overlaid based on their spatial information. So you are then able to see what is the place-based relationship across these different layers. So in addition to these examples that I just gave, we are also able to overlay, for instance, neighborhood boundaries with locations of crime to get an understanding of what that relationship is. So with GIS, we have this visual component. So we're able to have symbols that are representing data and information that is being presented on the map, but we've got also this database component. So we've got that location information. So where are these features located in the world? So where is that 3D representation on a 2D, or in some cases, if we have some X, Y, and now Z values, we can do some 3D imagery analysis, but also other attributes. And so attributes being fields and pieces in your data set that describe what we're seeing here. So in the example of transportation layers, we might have one that is showing street references. And so a attribute might be the name of a street. Another attribute could be the traffic volume. Is this a highway? Is this a secondary street that is used? And all of these things can be represented in symbols to make that visual component, the visual piece that drives a map. But this information and the location of these attributes and these values can be analyzed to tell a story or to answer a question using GIS. And so ultimately, GIS requires a lot of input data layers, references, and you can have your analysis as part of your geographic information system. So ultimately, you can just break it down. It's a visual mapped out component that you could look at, and a database that drives all of the spatial location information, all the attributes, and then all of the value analysis that you can conduct. So there's two basic types of GIS data, and I'm primarily going to focus on this first type of vector data. So vector data is represented in GIS in a few different ways. So you might hear folks talk about shapefiles. So a shapefile is not one specific file, rather a package of files, and .shp, .prj, .dbf, .shx, and all of these pieces in conjunction form a GIS layer. A shapefile, which was created by Esri and is heavily used for ArcMap, ArcPro, relies on, for instance, the PRJ file to specify what projection is being used for this data. The .dbf, this is a database file. It is a flat file of information, and you can also do some record linking of linking this database attribution information to other files. And the .shp, for instance, tells you what this literally looks like when you're pulling it into a map. And so we also have geodatabases. These are .gdb and GeoJSON files as well. These are other ways of storing and managing vector GIS data. So with this vector data, you have really three basic ways of representing data. You can have a vector file that is for point locations, for lines, or for polygons. So point data is literally just a point. It is one location, one vertex, one place with X and Y latitude, longitude coordinates that represents something in the world. And depending on your scale, it could be the location of a city, if we're looking at a country or a very large map that has that particular scale, or it could be something as small as an individual person, an individual house, a tree that might have been planted. Line files are ones in which you have multiple points, so multiple locations with latitude, longitude, XY coordinates, and there is a relationship between these points, one so that allows you to start drawing segments. So in this example here, in this visualization, we have three specific point locations that are connected to by two line segments, and there is a relationship. So some examples of line vector data would be a street. So if you are looking at a road, you have a starting point and an end point. And if there are any curves or turns in this road, those can be represented by additional vertices or additional latitude, longitude coordinates to help connect that start and that end point. A polygon vector file is one that has a minimum of 3 point locations, And in this example, we've got 3 points, 3 segments. There is a relationship between all 3 of these points, and they are forming a closed polygon visual. So some examples of polygon vector data would be boundaries of city limits. We can have polygons, again, depending on the scale of your map, that represent a building footprint or a land parcel in which there is development or activity going on. And so you're not really able to mix points, lines, and polygons if you have data that is of specific incidents or records that would only be in a point rather than line shapefile. Polygons stay with other polygons, lines with lines. That's not to say that we can't explore the relationship of points as they might relate to polygons or lines as they could relate to points. However, for each individual shapefile or layer that we're dealing with, we have to use one of these. Raster data is a bit different. So raster data can take a few different forms. So some examples listed here, we've got JPEG images, PNG files, TIFF files. And so raster data are images that are representative of the globe. So these could be aerial imagery that is captured by plane, satellite imagery. It is photographic in nature. And so it is represented with latitude, longitude coordinates. So what you're able to do is take all 4 corners of a particular image and georeference it and say each of these corners corresponds to this latitude, longitude coordinate in the real world. And then we are able to analyze data on here as each pixel has its own unique value. So each pixel could be representative of a color that could have a particular value. It could be data that is infrared. It could be LiDAR, so light radar data. And again, each pixel is coded to a value that corresponds to something. So if we're looking at, for instance, data that is looking at forest and tree cover in a state park that is raster data, we're able to identify different species of trees based on the wavelength of light that is being reflected in the imagery. So we're able to discern the differences between an oak tree and a pine tree. We're also able to identify the size of each of these pixels. So that allows us, once we know the scale, to say with confidence the size of features that we are seeing in the raster data. So raster data can interact with vector data. It is something that you can pull these different types of data into one system and do some basic analysis to, again, just have a better understanding of the data and the information that we are analyzing. So you may have already, even if you haven't known it, interacted with some GIS applications. So there are some desktop options and some online options for making maps and displaying your data visualizations. But oftentimes many people's first introduction to using GIS is through Google Maps, or if you are of a certain age, such as myself, familiarity with using GPS devices. So anytime you open up Google Maps and search for a particular business, for instance, or you pull up driving directions, that is using a GIS. Those particular services rely on street networks. So those oftentimes are line layers. You might be searching for a business. This could be being represented as point data. And we can think about attributes in that point data set being the business hours, phone number, contact information, the name, what type of business is it? This is all attribute information. And so you are able to really explore your world, use it for navigation, but it is a GIS system. So in terms of desktop software, there's a couple options, some of which that I recommend would be Esri's ArcMap, which is now being phased out by ArcGIS Pro. This is a for-cost option. There are student versions available. I believe currently the ArcGIS student license is $100 per year. This is software that is predominantly used in academic and governmental settings. The alternative, which is a free open source desktop software option, is Quantum GIS or QGIS. So there are some upsides, cost aside, to using QGIS. For many years, QGIS was really the only option if you wanted a 64-bit version to do your data analysis and mapping. QGIS offers versions that are compatible for Windows, for Mac users, as well as Linux users. Esri has not necessarily been available to folks that are Mac users, for instance. So a couple different considerations. The QGIS and the open source resources are primarily used by folks in the private industry. We do have some people in academic settings that are using QGIS, but if you are looking to work with a governmental agency and many academic groups, you are going to be experiencing Esri's ArcGIS Pro. In terms of online, Esri has an online portal, so their arcgis.com platform enables users to create free accounts. You also have access, if you are a paid subscriber to their desktop software, to have a lot of data analysis tools, but with a free public account through arcgis.com, you're able to make some maps, share them, embed them in your own website, embed them in a portfolio. So it's oftentimes a very easy, quick out-of-the-box solution for mapping. There are some other options if you are leaning more towards open source GIS, which would be Mapbox and Leaflet are fantastic resources. In addition to Google Maps and Google Earth, again, very quick and easy tools for using maps and exploring GIS data. I would be remiss if I didn't also mention OpenStreetMap. So openstreetmap.org is a platform that has been described by many as Google Maps meets Wikipedia. So it is a mapping platform that is international, that is open and editable. So this is a incredible value add to be able to contribute to maps. So if you see some incomplete attribute information, if you are missing locations on the map, with a free account, you're able to sign in and do some editing within your web browser to update and publish a new and better and improved version of your map. It is a great resource also if you are getting acquainted with GIS and would like to get familiarized with some basic drawing tools of drawing out lines and polygons. It is a resource that I highly recommend. There's also a lot of groups online that use GIS applications, share out projects, some meetup groups that get together to do focused and targeted work on OpenStreetMap. So I heavily encourage folks to just do a quick Google search and see what's out there and ways of experiencing GIS applications for yourself. So at the Baltimore Neighborhood Indicators Alliance, we do a lot of data work where we receive data that needs to be coded. So we have information oftentimes from a lot of our data partners and folks that create data and share it with us, information that just has, for instance, a street address and perhaps a city, state, or zip code. This mock example is 4 locations of restaurants. So we've got the Breakfast Cafe, Bob's Diner, Sam's Spots, McDonald's. So here I've highlighted a couple things in this data So under type, so I'm going to get started over here on the right-hand side. This here is an example of an attribute. So this describes the type of restaurant. So here we can see that both Sam's Spot and the Breakfast Cafe do breakfast and brunch. Bob's Diner serves food all day, but we can see here that we have a missing value for this McDonald's location. So in this example, we have a null value, so a blank value under type. So this might be a problem if you're seeking to do an analysis to describe the different types of restaurants you might be looking at. So when you have null values, it really prohibits you from doing any sort of frequency analyses, any other sorts of descriptive statistics. And if you're thinking about mapping, it also prohibits you from potentially plotting out these four locations and doing custom symbols to designate types of restaurants. So that's something to bear in mind. If this is data that you have not personally collected yourself, you never want to make some assumptions about the meaning of data. So oftentimes, incomplete as it may be, it's often best to just leave it as a null value. So moving over here to this street column. So street here is representing some street addresses. So here we've got a house number. So with this breakfast cafe, that's 123, the street name of Maine, and then a street type, which is in this case, street. So it's very important to have all of these elements in addition to street direction. So is it north or south, east, west? All of these pieces are incredibly useful when you're trying to identify these locations onto a map. So for this example that is circled here for Sam's Spot, the street is listed as 543 Potato. So in many places, you often do not have a repeating street name. However, in Baltimore City, where we are doing a lot of this work, we will sometimes have a street name that is often duplicated in the alley name. So sometimes, again, we can make some assumptions. We might not have or maybe we might have a restaurant operating out of an alley, but when we're missing something like a street type, is this a street? Is it an avenue? Is it an alley? It's best not to make some assumptions about what we've got here. We can see some variations in these street types here. So we've got the word street fully spelled out, 987 Fake Avenue for Bob's Diner. We've got avenue, the word abbreviated to AVE, and we've got a period after the abbreviation. For McDonald's at 100 Food Court, court is abbreviated without punctuation. So the good news is that in the process of street centerline geocoding, which I'll talk about on the next slide, is that it's okay to have different expected abbreviations. So we would expect avenue to be abbreviated to a standard AVE, court makes sense to be abbreviated to CT, and the punctuation actually doesn't make that much of a difference. But again, with this example of Sam's Spot, by missing the street type, that could lead to some problems when we're doing our processing. And we might have to do a little bit of work to figure out where exactly is this particular restaurant located if we want to get it included in our map and in our analysis. So street centerline geocoding is actually kind of a neat process. So in order to do this, you need to have some sort of a reference file. So for street centerlines, the reference file is going to be a line vector layer. So this could be in a geodatabase, it could be a GeoJSON file, it could be a shapefile, that this line data has attributes in it that describe ranges and ranges of house numbers, and then also street names, street types, and a bit of data that really is able for the system to identify how long is each street segment itself. And so we've got all of these pieces that are in here, and because a street center line, this reference file, is in a GIS system, there's inherently X and Y coordinates configured into it. So if you have your start and your endpoint, again, this latitude longitude coordinate of these endpoints or any vertices in the center has location information into it. So if you have this reference file in your GIS system and you have then an input file, so an example would be this restaurant example here. You can pull in those street addresses with the house number, the street name, the street type, sometimes direction. And what it will do is try to approximate or interpolate the locations of these street addresses in reference to this line shapefile center line. So in this particular example, we've got two addresses in this graphic, 48 Main Street and 95 Main Street. So the centerline file has built into it that our address ranges, and we can see these represented in red, they range from 1 to 99, or our house numbers. And so we have both odd and even house numbers associated here, represented on the left and then the right side of this street segment. So for 48 Main Street, number one, it's identified as Main Street, so it goes to that particular segment. If we were geocoding data that is Elm Avenue, it would find a street segment called Elm Avenue and match to that. And for the house number, it sees, okay, 48 is an even number. Even numbers go onto the right side of this street segment, so going to the right side of Main Street, and 48 is approximately halfway between this range of, on the even side, 2 to 98 Main Street. So it places a dot and creates a latitude longitude coordinate for 48 Main Street. For 95 Main Street, conversely, that is coming up as a 95 is an odd number, so it's going to be on the left side of the street segment. 95 is significantly closer to the 99 house number versus 1, so its interpolated point would be closer to the end point of this line segment. So we then have these different street addresses being placed on different sides of the street and placed based on that house number. So as you can imagine, if you have very long street segments that have a lot of address ranges, you might not have the same level of accuracy as you might get with a much shorter street segment with fewer ranges in the house numbers. So again, if you are of a certain age, or perhaps this still happens nowadays, if you plug in, for instance, an address to your GPS, I remember growing up, sometimes it would say your destination is ahead on the right in a quarter of a mile, and then I see my destination as I'm driving past. So for some reason, that GPS system thought that that particular address would be further down the road. The reason why that error happened is because it was using this interpolation process to approximate your location. Nowadays, a lot of these GIS systems in GPS devices and on Google Maps have increased accuracy because they're able to not only reference these street segments, but they're also able to reference point locations along the road. So that ends up being incredibly helpful actually for navigation. But so you're able to do this not just for 1 or 2 or 3 addresses. You are able to geocode if you have files with hundreds of up to hundreds of thousands of records. So imagine using Google Maps, for instance, instead of looking up one address, you're looking up 300,000 records. So this process can sometimes be time consuming because it is scanning the entire reference file for all of your records that you have in your input and creating these latitude, longitude coordinates and creating a point shapefile with these dots, these locations that are in your input. So if, for instance, you have a address that isn't being recognized by your reference, you do have the option of reviewing it and identifying, is this an address that is able to be mapped out? Perhaps there might be a misspelling. If there is an error in the street type or direction, you have the option to update that location information and perhaps get a new point that can be placed onto the map. So with this geocoding process, we now have a point level data set. There are a lot of point level data sets that have already been processed that are available on open data portals for you to use. And so these point level data sets have that very specific latitude, longitude coordinate set to represent locations. So some examples of point level data that the Baltimore Neighborhood Indicators Alliance uses would be locations of vacant properties or locations of violent crimes, for instance, locations of households with Enoch Pratt library cards. And so once we have data that is in a GIS system as this point level data, we're able to make some visualizations, we're able to make some maps, we can use different symbols to represent different attributes that we have in our data, and we are able to analyze different data types. So we can create symbols based on categorical data, nominal data, ordinal data as well. We're able to create symbols and make some visualizations based on time information as well, such as date and time of day. And so once we have data that is into a GIS system, we have latitude, longitude coordinates, we're able to analyze attributes, and we're also able to do analysis based on location. So we can do some functions like proximity analysis to see how close points are to one another or to other features that might be in a GIS. And we're also able to do a function called spatial join. So a spatial join is one that is incredibly powerful for us as an organization to analyze and create all of our community indicators. So a process that we use to create our indicators is one of data aggregation. So we are able to use in GIS a spatial join function that allows us to look at the spatial relationship of points that we might have. This could also be lines or other smaller polygons as they relate to a polygon layer of geographic boundaries. And so we are able to use the spatial location of boundary files, the location information in our point data, and we're able to then do an analysis. And so we are able to, for instance, append a neighborhood or a community name to that point level data. And that allows us to do things like frequency counts. We can calculate some rates or percentages, and we can use this data to describe larger communities. When we do this process, when we aggregate our data, we are able to take our point level information, and when we pull it into some of these boundaries, we can normalize data based on things like total population, which comes from the census, or total residential properties, a data set that comes from a work group called Maryland Property View. And so we're able to take then that frequency count, how many points in a polygon, and make a percent, make a rate, and this allows us to compare different geographic areas. So in this particular map here, the green dots are representing locations of foreclosure filings in Baltimore City. The orange shapes, the polygons, these are the Baltimore Neighborhood Indicators Alliance Community Statistical Areas, or CSAs. And so when we calculate our foreclosure filing indicator, what we do is we look at the count of these dots, so the count of foreclosure filings, and divide it by residential properties times 100. And so by dividing it by that total residential population, we can compare areas across the city to really see how they are doing in relation to that particular measure. So there are, of course, some caveats. In this map, for instance, we can see some areas over here in East Baltimore. I've got this area here that's south of the Pigtown neighborhood, this large area here. These are industrial areas, and then also we've got some park spaces. So we can think about how the land is being used as being kind of a predictor of where we would have a residential event, such as a foreclosure filing. But then we're also able to identify that there are some communities, particularly in North Baltimore, that don't have a lot of these instances of foreclosures. And so it's not necessarily a difference of land use, but it is a difference of this particular indicator that we're seeing, this data set in Baltimore City. So by analyzing and normalizing this data, we are able to kind of take into account the overall size. So some communities are larger than others, and we're able to take into account whether or not for this particular measure, any similarities or differences across. So as I mentioned, percentages and rates, the Baltimore Neighborhood Indicators Alliance uses a lot of these. So this is a count divided by a population. For percentages, this is times 100. For rates, times 1,000. So percentage indicators are fantastic if we're looking at representing a share of a population. So what's the percentage of properties in Baltimore that are vacant? What's the percentage of people age 16 to 64 that are employed? Rates are good at looking at instances of events or behaviors or occurrences. So crime, number of 311 calls to CityStat for customer service requests. These are great to look at rates because you may have multiple occurrences. You might have multiple 911 calls, multiple trash calls that could be occurring in neighborhoods. When you don't necessarily have a really good population denominator, be it in terms of human population or a residential or commercial population, it is sometimes acceptable to use a density calculation. So that's a number of counts divided by a square area, square miles, for instance. So this is oftentimes used as a measure for identifying population density, for instance. So really quickly, I want to have a brief discussion of geographic boundaries. So we're just talking about all this data normalization that can happen. And it's important to think about our different geographic levels for representing data and information. So at the largest scale in America, we have the country. So we are able to think about data, we're able to think about place in terms of the United States of America. The country is comprised of 50 states. So states being the next smallest geographic area that we're able to think about and describe using data. States are comprised of counties. In Maryland, we've got counties. The city of Baltimore, Baltimore City is a county that is represented. So within Baltimore City, it's located within the state of Maryland in the United States of America as the country. The Census Bureau conducts a decennial census. So every 10 years, they put out a form for folks to fill out, specifying their name. It has their location information, but then also providing information on race, ethnicity, and also on your age. And so the Census Bureau identifies that this information is very sensitive. Census data, so specific details of where people live, are only available 72 years after a census has taken place. So it is currently 2022. And so 72 years ago, the 1950 census was being conducted. And so we are now able to explore the 1950 census records. Because this data is sensitive, the Census Bureau has identified, for instance, 3 different census-based boundaries that are used for representing data. These boundaries are described and identified by the Census Bureau without any heavy local input from planning jurisdictions. There is a process of communication and coordination, but these are areas that are identified at the national level, and data from the Census Bureau around demographics from the decennial census, as well as the census's American Community Survey, are available at some of these other geographic areas. So once we're traveling down from country, state to county, we have census tracts. In Baltimore City, as of 2020, we have 199 census tracts. Census tracts are drawn really just based on where people live. It's an attempt to put together a few thousand people and put boundaries or polygons around them. So the census tract is a geography in which we are able to get some very detailed information through the American Community Survey, and specifically the 5-year estimates on things like socioeconomic characteristics. So at the Baltimore Neighborhood Indicators Alliance, we're always on the hunt for getting really good tract level data to describe places. Census tracts are made up of census block groups. So in Baltimore, we have over 700 block groups that are combined to make census tracts. And even smaller than a block group is a census block. In an urban populated place such as Baltimore City, a census block is almost really a city block. It looks a little bit different in rural areas, but a census block is the smallest level of data that you can get right now for the 2020 census, the decennial census. So for instance, we have for 2020, the census blocks in Baltimore City and the total population and race ethnicity for the blocks. Block groups are kind of an intermediary step. We are able to get some data at the block group level. However, whenever we're using data from the American Community Survey, oftentimes because it is a sample survey that's only sent out to a small percentage of the population, sometimes we have very high margins of error. So census tracts are a really good option for us as we're analyzing data. So I want to make mention of FIPS codes. So FIPS codes are a federal identifier that really describe the geographic levels that we have. And these are used pretty heavily in a few different places, but you will find this if you're using and analyzing census data. So the state of Maryland has a code that designates it as 24. Baltimore City is coded as 510. A census tract, for instance, and sometimes we have some leading zeros here. An example of one in Baltimore City is tract 102, which is represented with these 6 digits of 010200. And then, for instance, we've got within that census tract some multitude of block groups. So these are identified usually as block group 1, block group 2, block group 3. And so if we were to go to the Census Bureau's website, data.census.gov, and we were interested in downloading 2020 population data for Baltimore City, we would want to be looking and filtering for data that is 24 Maryland, 510 Baltimore City. And then when we download the data, we would have data values for these particular FIPS codes described in this sort of way. So it would be a text identifier for this particular block group. The example would be 2451001020001. So because these are text strings, we have some leading zeros that often occur with census tract numbers. You want to make sure that when you're opening and looking at this data, that you try to keep it in a text format, not a numeric format. So incredibly important as we go along. So you were able in GIS to aggregate data to all of these different levels: census blocks, block groups, tracts, counties, states, and the country. But you're really unable to get that specific address level data to come through when you're analyzing that level of data, but you are able to get some already aggregated statistical information from the census. And if you're interested in making out some community indicators, it's often just incredibly easy to use some of the census based geographies as a way of easily getting population information. So if you have other data sets and you're trying to do that analysis, you've got your point level data, trying to aggregate it to a geographic level, you might want to think about using some of these census-based geographic areas because it makes creating those rates percentages really easy. So really quickly, I want to make mention of zip codes. Zip codes are actually not polygons. Zip codes are not clear-cut geographic boundaries. Zip codes cross multiple jurisdictions, so they are not specific. They do not nest perfectly within counties. In the city of Baltimore, we have some zip codes that extend out into Baltimore County. Likewise, we have some predominant Baltimore County zip codes that extend into Baltimore City. Zip codes are created by not the Census Bureau, but the United States Postal Service. And so zip codes are honestly actually lines. They are based on the route deliveries that are being used by postal workers. And so while folks might not necessarily know what census tract they live in, people generally know what zip code they live in. So it can sometimes be tough when you're analyzing data because zip codes are great. People are able to easily understand and identify zip codes. But if we're looking at data, for instance, just for Baltimore City, it becomes really messy when we have zip codes that extend out into Baltimore County or vice versa. And zip code geographies are actually pretty large, and it's sometimes really difficult of discerning spatial patterns in data when we're looking at very large geographic areas. So let's keep talking about geographic boundaries while we're on the subject. So the city of Baltimore uses a geographic boundary called neighborhoods or neighborhood statistical areas. These are defined by the Baltimore City Planning Department every decade. Sometimes they make some tweaks to the boundaries of these neighborhood statistical areas. Sometimes areas are combined, sometimes they are split, sometimes we have name changes. But census blocks, so again, those absolute smallest levels of census geographies are used, they are combined to create neighborhood statistical areas. So the city of Baltimore is able to get some very basic decennial census data to describe neighborhoods. They are able to pull in total population, race and ethnicity information, and they often work with the US Census Bureau and will contract the Census Bureau to create specialized neighborhood statistical area profiles that combine census blocks. Oftentimes, because the census has this data already in their own institution, rather than share sensitive data to another external agency or organization, they will do that analysis in their own departments. And so again, the city of Baltimore contracts with the Census Bureau to every few years get some demographic descriptive data for their neighborhoods. Neighborhoods are a unit here in Baltimore that people frequently identify with. People generally are familiar with the names of their neighborhoods that they're in, but neighborhood statistical areas can sometimes be very small. We have nearly 300 neighborhood statistical areas in Baltimore City, some of which are residential areas, but some of which are parks. So Druid Hill Park, Patterson Park, these are park spaces, but they are still considered neighborhood statistical areas. Same thing with industrial zones. Sometimes even residential neighborhood statistical areas are very small. So for instance, in North Baltimore, there is one that I believe only has 7 or 8 residential properties located in there. And so if we're trying to calculate rates and percentages and densities, neighborhood statistical areas might not be the best for analyzing longitudinal data across time because really, really small areas are subject to outliers sometimes in data. So very high values, very low values, are really able to sway and influence sometimes the rates and percentages that we calculate. So the Baltimore Neighborhood Indicators Alliance will occasionally work at this geographic scale, but it is not one that we put out open, accessible community data for. The Baltimore Neighborhood Indicators Alliance instead focuses and uses and has used for over 20 years now the community statistical area. These are custom geographies. These are aggregations and clusters of census tracts. So again, for 2020, we have 199 census tracts in Baltimore City. A committee of stakeholders over 2 decades ago created the original boundaries for the community statistical areas. And what they've done and what we've done in previous years, in years since then, in 2010 and again in 2020, is to look and see what sorts of communities and data sets are being represented in these tracts. So the idea was to combine census tracts that had similar demographics and similar housing types into these community statistical areas so that they can be relatively similar units of analysis. So for Baltimore City, we have 55 of these community statistical areas. And again, they are based off of census tract boundaries, which are defined and set by the US Census Bureau every 10 years. So in addition to the Baltimore Neighborhood Indicators Alliance, you will find some other folks using CSAs. So because we have open data sets, oftentimes a lot of faculty and student researchers at universities will opt to use the community statistical area. And we have also been working with the Baltimore City Health Department. They have used the community statistical area for reporting out some of their community health profiles for many years now. So here's an example of a community indicator being represented at the community statistical area. So data is available and it is on the BINIA website as well as BINIA's open data portal that has values for our 55 communities. And so once we have values that are being representative for these polygon areas, we're able to make some maps. This map is one that is known as a choropleth map. So this shows our 55 CSAs and the values of this indicator, percent of residential properties that are vacant and abandoned, that value for these 55 communities is put into a system, and the symbol that is created for that community is based on the value of that indicator. And on this map, the lightest shades of this pinkish red have the lowest percentage of properties that are residential properties that are vacant and abandoned. These darkest colors in West and then East Baltimore have the highest percentages. Oftentimes, choropleth maps use around 5. The standard is between 3 and 7 different classes or categories in representing data. And it's a way for users to visually see, just eyeballing maps, some of the similarities. So areas that have the same color are in the same class or the same category. So they're similar in regards to this particular measure. And communities that are a completely different color are measuring very differently on this measure. So again, this data was used, residential properties that are vacant, that was our numerator. We were able to calculate the count of vacant property dots for these CSA polygons. And then we were also calculating the number of residential homes, again, dots, calculating what's that number for our CSAs. And then we divided residential properties, we divided vacant properties by residential properties times 100 to get this data. So there's a lot of other different types of spatial analyses that can be done with point level data, with polygon data, with data that is already summarized and aggregated, such as data from the Census Bureau and the American Community Survey. We can do all sorts of hotspot densities. So looking at clusters of points on a map, we can do analyses to find nearest neighbor. So we can take a look and identify different spatial patterns and trends in a data set, within that one data layer, and then think about how it might relate to other spatial inputs. We're able to do some geographically weighted regressions. So if you think about regression analyses that you're able to do in other statistical packages, we can do it in GIS and use spatial location and proximity to other units as a variable in our analysis. We're able to do other analyses such as a proximity analysis and buffers. So for instance, we can do an analysis to see how many trees might have been planted in a half-mile intersection of two streets in a particular neighborhood. So again, all of these are analyses that can be conducted using that great vector GIS data, points, lines, polygons, to really have a deep understanding of trends that we're seeing in Baltimore City. So I'm going to close out with sharing out a few GIS resources. So the first two listed here, we've got Open Baltimore, and then we've got Maryland IMAP. These are respectively the city and state's open data portals. So data.baltimorecity.gov and then data.imap.maryland.gov. These are places where you can find individual record data sets. The city publishes out locations of city assets, so things like street networks, locations of parks, but then we also have data around crime, housing, 311 calls. Maryland IMAP has some great state level published pieces of information. Ones that the Baltimore Neighborhood Indicators Alliance have used have included COVID data, so data on number of cases by zip code. We've used some data that's provided by the MTA on bus ridership and other transit ridership. We've used Maryland IMAP to download parcel information and data.census.gov. So this is where you're able to get that Census Bureau data, data from the American Community Survey on all sorts of demographic, socioeconomic status, housing, and employment information for communities. So this is all, these three are all open sources of data and information. This is information that is accessible for people to use. And so, as I mentioned earlier, there are a couple free open source options. So QGIS is that free desktop mapping software. Again, it's available at 32 and 64-bit options. You can access it regardless of if you're using a Windows PC, a Mac, or Linux. And then arcgis.com offers a free online public account that allows you to upload, to visualize data, and to create specific map visualizations that can be embedded in websites, that can be used in driving a spatial portfolio if that's what you're interested in doing. So these are some resources that I personally recommend. These are ones that I use both personally when I am working on a mapping project, or that I use professionally through the Baltimore Neighborhood Indicators Alliance. So I hope these were all resources and slides that were useful in thinking through different spatial concepts and these applications for the Baltimore Data Science Core. Thank you.